we are all here to talk about the calculus portion of the class. Now, just to make sure it's clear to everyone, the Physics 251 class is calculus-based physics, but we meet for 3 days a week with the algebra-based people. And so we'll only be talking about the calculus ideas in class here on Tuesdays. I will go through a few more things on the syllabus for lab today, because it turns out I didn't cover everything I meant to yesterday. I kind of got pulled into things. So I don't know why I have this here. Don't really need that. What I need is today, what we're going to do is we're going to just review some of the calculus things. We don't have any physics yet in the class, right? Yesterday I just talked about the syllabus, and then today in lab, we'll learn a little about units and stuff. But for today, I want to make sure that we talk a little bit about the calculus that we're going to be using throughout the school year. Now, I know 3 of you you guys just finished Calculus 1, and 3 of you are in Calculus 2, right? Yeah. And you decided not to take it. Yeah, Kaylin, I just want to make sure is there T or not in it. Okay, so anyway, your calculus is, developing. There are some things that we do in this class that are beyond what you've learned. And so I will try to introduce those things when we get to them. And today I'm going to go through all of the variations of calculus we're going to use throughout the school year. It's arranged actually in chronological order of when they'll come up. So I can draw a separator. This would be first semester. This would be second semester. So the very first thing we're going to come up to is what we have right here, these little derivatives. You've all learned how to do a derivative. Well, one of the reasons I think the calculus-based physics is easier to understand is because these relationships between the position, the velocity, and the acceleration are very simple mathematical relationships with calculus. If you don't have calculus, you got to do a little hand waving to get to how they relate. So we have simple relationships. V here, if it has an arrow over the top, then it's a vector. That means it has direction. No arrow over the top, then it has no direction, then we call it the speed. So speed is without direction, a scalar value. With the arrow over it, it's velocity. So we have different names for if it's a vector or not. You'll find that I mess it up all the time. I try not to, but we use them so often I get them mistaken in my speech. So the V stands for velocity. That's why I have V and not S for speed. So speed is the derivative with respect to time. Now in physics, we won't use this much, if at all, but we have a shorthand way of writing a derivative with respect to time. If it's derivative with respect to time, we'll put the variable with the dot over it. So x dot means a time derivative. Now, what did you use in calculus class as a shorthand? You used a prime. You did something like y prime equals, and what that was dy dx. And we still do that. The prime means it's derivative with respect to position. So primes we use in physics for positional derivatives. Dots we use in physics for time derivatives. So these two equations, acceleration is dv dt, the derivative of the velocity with respect to time. But since velocity is the derivative of position with respect to time, then you can replace this equation here. I'm just going to expand on what's written right there. I told myself I was going to write neater this year, trying to use letters in the English language. Oops. Instead of V or X, I put. So that's substituting what V is into the equation. And then when I take that d of dx dt we actually usually write it like this. It's the derivative of x with respect to time twice. And so we combine that. We have the derivative of the derivative is d second x. And then since it's with respect to time squared, nobody ever writes a parenthesis like this. But that's why you have d second x dt squared. Because you're taking the derivative of x twice, the first time with respect to time and the second time, again, with respect to time. You can have other kinds of derivatives. You can have like d second x d. It's possible to have something like this. And what that means is you're going to take your function x and first take the derivative with respect to x. And then from that derivative, you're going to take the derivative with respect to y. So just a little bit to explain the nomenclature and how we have the equivalence, that the derivative of velocity with respect to time. By the way, v subscript x means the component of velocity in the x direction or the speed in the x direction. We break our directions into three perpendicular directions, which traditionally we just call x, y, and z. And so the x is just specifying the direction. So let's look at how these are used. So often you're given x of t, and then you find v and a. So let's take a simple function. Let's suppose that my position as a function of time, so the x parenthesis t means x is a function of time. It can be confusing because it could also mean x multiplied by time, right? The same way of writing things can have different meanings. But when you're writing a function, that parenthesis something means this is the variable of the function. So let's say my function is ct cubed. If I want to find the speed in the x direction, so first I write my definition so I don't get confused. So I need to take the derivative with respect to time of ct cubed. Now you've all learned a calculus rule for how to take a derivative of this. I like to call this the polynomial rule. I have c. What do you do with the constant when you take a derivative? It doesn't change, right? By definition of constant. So it just moves through. It's not affected. So the c is just going to remain as is. But then time is the variable that's changing. And so I have the derivative of time cubed with respect to time. So that's a polynomial. What was the rule for taking derivative of a polynomial? Bring down the exponent first. So I'm going to bring down the 3. Now that parenthesis meant times, not a function of. And then what do I do after that? Subtract 1 from the exponent. And so that's going to be 3ct squared. And now if I want to find the acceleration in the x direction, I have, what's my constant in this function? Not just c now, 3c. Because the 3 was also constant. I mean, it's always constant. And then the derivative of t squared using the same rule. And so there's my acceleration.
So it's basically double prime for the whole thing?
Well, it's double dot because it's time. Okay. But yes, that's correct. So here we've done a simple function. and found the derivatives. That's one way we can use it. Notice that's item 1. Second one is I could be given v of x and find a. Well, that's really fundamentally part of what I did. I just had to calculate v. But then I can be given the acceleration and find the speed and the position. Now that's a little different game. That's right. We're going to use what we call differential equations here. First, I'm going to maybe page manipulation, insert a page, I'm going to actually insert 2 pages after page 1 in white. I believe that worked. Good, it worked. So let's say that we start with the common situation. If I take this pin and I let go, its acceleration is constant. And so I'm going to start with an equation that is the acceleration is equal to a constant. So a different C from what I used before. And now I want to find acceleration in the x direction is constant. What is v of x? So Nathan said we're going to integrate. I'm going to go through the steps here for how we get there because, like I said, it's technically differential equations. So our equation was excuse me. The first thing I have to do to find what v is to change this equation so I have my variables separated. Now, I'll substitute for ax because you can't really separate the variables until you've done that substitution. So what are the variables involved in this equation that I've written down? Okay. There's another one, and v of x. So I need to separate variables. Okay. Is it A or E? SCP-A or SCP? It's A, okay. You see, I have both of them written there, so I had to be right one way or another. Okay, so I need to separate variables. That means I need to rearrange this equation so one side of the equal sign has one variable, the other side of the equal sign has the other variable. So in this case, that's pretty simple. Let us suppose here that, well, let's suppose, we don't have to do any supposing. There's one more thing with the separation of variable. Not just do I separate them, but I must have D on top. So when I separate them with the rule that D's on top, there's only 2 ways of separating them here. First of all, to get the D's on top, what would be the first step you would do? Now the D's are attached. You can't separate the D and the V or the D and the T. They're attached. It's one thing. So what would you do to separate them? Okay. Now Nathan did 2 steps there. I'm just going to do 1. The first thing I'm going to do is multiply both sides by dt. Now a purist will say, well, now this was a derivative. A derivative is one thing. dt is a solo thing. It's part of the derivative. But in fact, that d means change. The difference in lowercase d and a capital delta that we'll be using in the non-calculus class is real simple. When Isaac Newton went home because of the Black Plague, greatest thing that ever happened to him, he was working on physics stuff, and he realized that he had stuff that was changing with minute continuous changes. And there was no math to deal with minute continuous changes. So he invented a new kind of math that we call calculus. He called it his math of fluxions. And then there was it Leibniz, something like that? Starts with a French guy, who read that he had said, I found this new way of math, came and talked to him, came up with some nice nomenclature and wrote about it. So he was the first one to actually write about calculus. And then there was, until the death of both of them, the big controversy over who invented calculus. The person who actually came up with the idea, the person who first published about it. Because Newton really didn't. He makes me look gregarious. He was very reclusive. But the fact is that dt just means a minute change in time. And so we're just using it like these are fractions, a minute change in speed divided by a minute change in time, because that's what derivative really means. So we multiply the dt across, and then we have canceling. So this dt and this dt cancel, and then I have c dt is equal to dvx. Now what Nathan said was divided by c. That's also correct. There are two correct ways of writing it. And so I'm going to leave it like this because I want to solve for v. So I'll leave the c on the other side because I want to solve for v. Now, if you look at this, the right-hand side is only dependent on speed, the x, speed in the x direction. The left-hand side is only dependent on time. We have two functions of different variables that are equal to each other. The only way this can be true is if they're truly independent, so I can simply integrate the left side and the right side. And if I put limits that match, limits. In physics, we almost always have limits on our integrals. In calculus class, my experience was we almost always didn't have limits on our integrals. So we have limits, so I'm going to be going from time initial, which for convenience, because you can choose when you start your clock, we say time initial is 0 almost every time, to time final. And then my speed will be speed initial to speed final. So as long as my speed initial is the speed at time equals 0, and my speed final is the speed at time final, then this is still going to have to be true. And now I have two really easy integrals. What's the integral of c dt? C is a constant, so how is a constant affected by an integral? It's not. So the c is going to remain. What's the integral of dt? Just t. So I'm going to have time, but then I have to put my limits. We generally show the limits like this. So there's the left side. The right side is even easier. Why is it easier? Because there's no constant. You just have integral of dvx, which becomes dx with our limits. So now when you have the limits, you have to evaluate those limits. And so I'm going to have put your upper limit first. So ct final minus, and then put in the lower limit, c times 0 is equal to upper limit. And now I have an equation for the speed final as a function of the time final. When is final? It's whenever I choose final to be. It's a variable, right? And so I'm going to do, through the magic of erasers, erase the finals there. Now it's a function that works for any time t. Finally, just solve for v. So I have the speed as a function of time is equal to initial speed. I just added v0 to both sides, plus ct. So now I found the speed as a function of time. I'll go ahead and put a subscript x there because it was in the x direction because I started with acceleration in the x direction. Now that I found the speed as a function of time, I can go one step further and find the position as a function of time. So I've gone through one step. Let's turn it to you as one big group. Given this here, find for me position as a function of time. So I'm going to have the four of you work together as one group. You all can put your minds together how you think you're going to do that. I know I could do 2 and 2, but and if you have questions, just ask them. I forgot to give you guys hand out for it. And then I have help beside as well. When you're separating the variables to do the integration, yes. Obviously, the derivative is not, so we can separation. Remember your team, you can talk to each other.
Wait, so basically you're finding how to find how to find x.
Yeah, you want to find the position as a function of time, given this function of speed as a function of time. Here is your analogy of what we just finished. What was our first step? Okay, we substituted, the first time we had AX and we substituted AX as dv dt, so we eliminated the variable we don't want. So now what variable do we want to substitute for? from. Which of those variables, what variables are in that equation? Speed and time, those are the two variables. And keep in mind, V0 is not a variable, that's a constant, it's the starting speed. So it's Vx and t are the two variables. Which one do we want to get rid of? We want to get rid of Vx. So what is V of x equal to? It's dx dt. So that's your first step.
How did you find that?
That was one of the definitions.
Oh, thank you.
Wait, so again, okay. So which one are we getting rid of?
The Vx.
Just the Vx.
Yeah, well, Vx is a function of time, right? That's all one thing.
Okay.
Vx is Vx is a function of time. So this is correct. Can't see. So this is, yes, that's Vx.
Am I allowed just to replace the Vx with the dt and keep the t here? Or
Um,
am I not?
You
Is that
usually don't write the t, because remember the t was just as a function of time.
Oh,
This
it's
is indeed a
I
function of
forget.
time.
It's a multiplier.
Yeah, it's not
Thank
multiplying.
you.
That's a complicated factor, right?
Yeah.
Okay, so it's all
Okay.
one.
Yeah, the Vx parentheses t and Vx are identical.
Okay. And we're just replacing it with.
So we have dx dt is equal to okay. So I know these three have the same thing written down. Oh, she's got a step further,
I don't know. I'm just guessing at this point.
and
Because we have to separate them onto different sides, right?
yeah, that's the next step.
Okay, so this is correct.
Why are we
Yes.
separating them exactly? Just
We're separating them so we have one side the equal side that's a function of only one variable. The
Okay.
other side is a function of only a different variable.
Okay.
And then they're independently equal, we can integrate both sides.
Okay. Oh gosh.
This should be CT and parentheses DT.
Oh, okay, yeah.
And, oh yeah, that's a plus sign addition.
Yeah.
So then you parentheses around everything with DT.
Oh, okay. That makes sense.
Integral. And remember, first you have to separate the variables. So you need to get the DT over here.
Oh, just the Vx. Okay.
The whole thing. I know. I only practiced derivatives with you. I didn't.
I don't remember any of the integral rules. Like I was so bad. Okay. So let's get rid of the
And that's what the homework assignment is, practicing your derivative rules and integral rules.
Good. Cool.
This one should be XCD. Okay,
Isn't it?
it's just DX. Yes.
Just the x is dx. Or is it just x?
Well, it's okay. You multiply. So this is-
Oh, okay.
I can do this. Well, no. This here is fine.
That would be.
Right, because you multiply both sides by t to get to this point. No. Now we have integral dx. What's the integral of dx?
Oh, it's just that.
Yeah.
Wow.
Question, so this will be gone, so the type is just,
Just the tt. The dx is still there.
okay, the answer will be there, and then this one, so.
Oh,
Are these constants next to the same or no?
The v0 is constant, the c is constant.
So can I just
So
put
T
down
is
the
not
same
constant.
when I integrate them?
The v0 and the c, yes, but t is a variable, so.
Okay, so.
I have to do something. I don't.
Constant.
You take the integral of both sides.
Yes.
How do you-
Like that is all over the place.
And now, once again, yes, we should have limits going from x initial to x final and time initial 0 to time final.
What time? Would it just be time then?
Well, the easiest, let me write this part just to make sure, because you're rusty on your calculus, it's been a while.
Yeah, sorry.
So you have, everybody has integral from time initial is equal to 0 to time final of v initial plus ct dt. It's easiest, especially when you're beginning, to not get confused by separating this into two separate variables. Now, let me point out some really important things that different people will gloss over. These parentheses here were very important. You can't put integral v0 plus ct dt, because mathematically that would be nonsense. The way we parse math, if we didn't have these parentheses, it'd be integral of v0 without respect to anything plus ct dt without an integral. Right? It just wouldn't make mathematical sense. So that parenthesis is very important for it to make mathematical sense. And then that allows me to just use the distributive property of multiplication to separate it into two integrals. Actually, I shouldn't say of multiplication, I should say of integrals. And then each one of these, I believe you can do on your own. I believe. Let's poll people. I will start with my physics major here. I'm sorry, but I have to. Yeah. Start with my physics major. How do we integrate a constant?
Wouldn't it stay the same? Wait.
It doesn't stay the same. When you have a polynomial, which a constant is essentially a polynomial with our variable having a power of 0. So no one ever would write this. Even on this assignment I'm giving you, I wouldn't write this. But integral of v0 dt is the same as writing v0, it's a constant, integral of t to the 0 dt. Right? Who's ever going to write t to the 0 to mean 1? Right? Nobody would do that. But that's effectively what it means. And when you're integrating a polynomial, you have the reverse of the rule we had for differentiating a polynomial. That is, when we differentiated, we brought down the power, and then we lowered the power by 1. Now we do it in opposite order and reversed. So now we're going to raise the power by 1. So that would be t to the 0 plus 1, and then divide by the new power. And like I said, no one would ever write t to the 0. It just is ridiculous. But you can see why you get that outcome by writing it. And so t to the 0 plus 1, that's t. Once again, nobody ever writes t to the 1 either. That's just t, and divided by 0 plus 1, that's divided by 1. So it's just t. So the first one gives you v0 times t with our limits. So t final minus t0, which is 0. What about the second term then? If I say ct, what's the power for t? So when I integrate, what's going to happen to the power? It's going to go up to 2, and I divide by the new power. Divide by 2. Now, in case you ever get confused on this, remember the fundamental theorem of calculus. The derivative of the integral is your original function. That's the fundamental theorem of calculus. And so that's why the steps were in the opposite order and reverse. Instead of going up, you go down, So you get back to the original function. So now I haven't finished the problem out, but we're close enough. What do you get? Whoever gets the answer first here, now you are a team, so you can lean on each other. Let us know.
CT, is that multiplied or they?
See that.
C is a constant.
So they're-
Because you're finding it below.
You find this interval and this interval. Then we apply limits, and we have our final equation. Okay. She has her final answer.
I'm done?
Yeah.
Oh,
Well, you're done because the T zeros make it,
Makes
minus
sense.
0, minus 0.
okay.
And so you do have on this side, x final minus x initial equals.
Okay, wait, so I need to do it again?
When you put in your limits,
Mhm.
you put the upper limit first, so x final.
X final, minus X initial.
Make sure it's a substrate that matters.
And to this is.
And remember, technically, this was v0t minus v0 times 0, plus c t squared over 2 minus 0, when you put in the limits.
X final minus X.
Well, for both of them.
Oh, I did, no, I did do that.
Yeah, that's. And so the t zeros are just zeros, and so that's just put a final and a final, and we have minus zeros. Well, I'm sorry,
Wait.
on subscripts on the t's.
Because these just are zero, so they don't count, right?
They're zeros, so you can add 0 to anything, it doesn't change it, right?
Still not sure what I got to, but okay. And then we wanted, what did we want?
Okay, so the final thing is just, you're solving for x, so you drop the f's. Yeah, I just had you write the f's, and now we're gonna drop them, but you have to move the x0 across the sign,
Okay, so it's raised to power of x.
the new power.
Okay, so we're having to
T squared,
t squared over t
over 2, over 2.
and this one's
Make sure you use such, because we set 0 9. And remember, you're integrating this side too, so the integral here is. You've already done the integrals here, so right.
Okay.
Or actually, maybe you only did this, you didn't do that one. Yeah, okay, so I'll just do this.
And then
And this is something about that.
This term here, it's t sub f, not t squared over 2 and a half.
Oh, yeah, no. I'm reading it.
And t initial is 0, so this one is 0.
So this one's 0.
Maybe we should show an arrow to 0 so you understand
No,
why.
I'm just trying to put.
What is the
So then, how do you have the one?
No, this stays the way it is.
So it's just.
I drop off the f after I'm all done.
So you drop off this stuff.
Yeah, so this whole thing goes to 0.
Okay,
And
then you,
this one I drop off.
okay, so this whole thing is 0, okay, so it's this.
this big one.
Well, it's still, this is v subscript 0, not v.
Big
Right, and so it was time raised to the 0. Remember, I went through that. The integral of dt is just t. So when you do the integral of dt, you're gonna have t. So just t. Well, yeah.
Like, trying to figure out how. Yeah. Like.
Trying to figure out what you did.
Yes. If I were to have the whole.
Okay, so on this side, I drop the F as well.
Yeah.
And then,
Great, but make sure you keep the x initial.
Okay, so just X.
And, well, move it to the other side of the process.
But then won't that be exponential? Or that should be,
I'm missing something else.
Yeah, you are missing something. Because of the time, I'm gonna come back up to finish it out. Because we've only done this and we haven't gotten to all the rest of the math we're gonna be doing. So here's the work that you should have. Starting with dx dt is equal to v0 plus ct. So the first step was separating the variables, multiplied both sides by dt, and then we say, aha, I have canceling going on, and so I have dx is equal to and then I integrate both sides independently. So everybody I'm reviewing how we got there. So you'll know, Taylor. So we first separated the variables. That's what I did with the blue. And then the green is writing what I had after separation of variables. And then with the red, I put in the integrals because now we have two sides that are independent of each other. So I'm integrating the two independent sides. And then doing those integrals, and I only have like 4 colors here, so I just don't have much cycling. So in black, I'm going to have the integral of dx is x. Integral of v0 dt is v0t. And the integral of ct dt, as we went through carefully, was ct squared over 2. Go ahead.
So the CT squared over 2, you would, okay. Would you add the 1 that is on the C, like the T over there, like that's technically a 1 in the corner, right? So you add another 1, you make it 2 over 2, and then what happens to the dt? That just goes away?
That's part of the integral is getting rid of the d. That's
And that gets rid of the t along with it, or it'd be,
well, the dt. So we had t dt. When you integrate t dt, that becomes t squared over 2.
okay,
So it's part of the integral for the d to disappear.
okay.
Now we plug in the limits, and this is where your work was a little fuzzy. So if you're trying to figure out where, this would be the only place that I didn't see you had written down clearly. Putting in the limits, I have x final minus x initial is equal to v0 t final minus v0 times 0 plus c t final squared over 2 minus c times 0 squared over 2. Notice this was the upper limit. I'll write the words down here. Upper minus lower, and then again, upper minus lower. So I did the two terms separately.
On each, so each term get its own limits that you subtract.
Yes.
Okay. And it's final minus its initial on each one of them.
Nathan, let me write the last line and then I will explain, I'll answer your question. So now for the last step, I just added x0 to both sides and removed the ones that are already 0. Okay, Nathan, what was your question?
How did you get the CT squared over 2?
So that was integrating. Now I'm showing this without limits here just to make it simpler to write. So integral of ct dt, the c is a constant. So I just write that down first. And then t means t to the 1. No one writes the 1 because it's ridiculous. But that's what it means. And so I'm going to have t to the 1 plus 1, because that's the rule for the integral, divided by the new power of 1 plus 1. So that's CT squared over 2.
So 1 plus 1, that is,
I took the initial power of 1 and then I raised it by 1.
okay.
And as you get into this, it'll become really second nature, but you have to practice a lot. You did some practice in calculus, but basically you were zooming from one topic to the next, right? Just like we do in every class. And so you'll take more practice for it to become second nature. This here, dropping off the F's, is the kinematic equation that we use 90% of the time. The position is equal to the initial position plus the initial speed multiplied by time plus 1/2 acceleration multiplied by time squared. So it simply came from integration, this kinematic equation, not some crazy hand-waving thing. It came from the definition of what speed and acceleration are. Now I only have 2 minutes, so getting back on topic. Other things that we're going to be doing, some of these sooner, some of them later. Finding extrema, that is if you have a function f of x, the extrema are the maxima and minima. You guys might remember me sitting in on some of your classes last year because my son was a senior in high school in your class. And I remember you guys going over this in calculus class, so I know you did it. I actually had the advantage of knowing, yeah, you guys have done this. So to find the extrema, I have a function like this. The extrema is the plural of extremum, which is a maximum or a minimum. So the extrema, there's a maximum, there's a minimum, there's a maximum, there's a minimum. What all those have in common is the slope is 0 because you were going up and now you're going down, or you were going down and now you're going up. So mathematically, we can find those by taking the derivative, the slope, because the derivative is the slope of the function. And if the slope is 0, if the derivative is 0, then you're at an extremum. And you can differentiate which kind of extremum by taking the second derivative. And this is what my math teacher taught me. Happy face and frowny face. So if the second derivative is positive,
Happy guy looks like he's dead.
if the second derivative is positive, smiley face, it's an upward curvature, which means that it is a minimum. And if the second derivative is negative, it's the frowny face, it's a maximum. Wasn't my teacher slick with this? I so don't look impressed. If the second derivative is 0, it's going to take a little more work. Second derivative being 0, it could be a local minimum, a local maximum, or it could be an inflection point. Inflection points are places where it goes like this. It's going down on one side and up on the other. Okay, so we'll have that. Then we'll have things like this. Integral of vectors. Vectors have direction. Now, what I show here has a dot product. Dot products is multiplying the parallel parts of vectors. So we're going to have to do some of this algebra idea of a dot product as well, because most people don't remember what a dot product is if they ever learned it. Then we have this function here. You probably haven't seen that function. That function is a directional derivative. And we'll learn about it later, but that's something we're going to have, is this directional derivative. And then moving on, we will have wave equations. Look at these beasts. Those don't make me happy. These are second order linear differential equations. Ain't one of you that's learned how to solve a second order linear differential equation. Second order because it has second derivatives. Linear because you don't have any that are like x squared or y squared or t squared, or x times y, So these kinds of things, all you're going to have to do is to see if the function fits. You'll have to calculate the derivatives and put them in and see if it's correct. So I'll give you an equation, say, does it fit? This curly thing, you guys haven't seen that, have you? But it's a beautiful thing. It's a simplifying thing. That's not hard, that's easy. When you have the curly, and actually it needs to have the curl coming this direction on the top, derivative, that means a partial derivative. I have the word partial written somewhere here. Partial derivative. And partial derivative simply means if you have a variable in the function that's not the one down here, it's constant for the purposes of your derivative. So if I have a function y that has two variables, and I have partial of y with respect to time, the other variable I'm treating as a constant. When you take derivative, if it's a constant, it just doesn't change, right? So it makes life easier. So when I see those partials, I get happy because it's an easier kind of derivative.
So which one is the constant?
Anything that's not, in this case here, it's the derivative of y with respect to time. So y here, it doesn't say, but y is a function of x and t. So in this one here, since it's derivative with respect to y, x will be a constant. And on this side here, it's a derivative with respect to x, so t will be a constant. So it just makes your calculation easier. We'll look into, right, when these come up, we'll do it again. I'm just pointing out the things that are going to come up. Thermodynamics will have some inexact differentials. Heat, you probably don't know right now, but heat is amount of energy that's transferred. It's a transfer. You don't have a change in transfer. It doesn't make sense. And so that's why it has the D with a slash through it, because it doesn't quite make sense. And then second semester, so this is second semester here, we'll have electromagnetism, and we'll have crazy old things, line integrals, integral of a cross product for the Biot-Savart law. Yeah, it gets more complicated there. And in quantum physics, we'll have a little more fun stuff here. That's the physics we're going to do. Now, I gave you a homework assignment. I'm rushing right now because, of course, we're pretty much out of time. Homework assignment is right here. This homework assignment is practice calculus. And I want you, in this assignment and this assignment only, to show me the brutal, gruesome details of how you did it, name your rules you used, right? Just because I want you to think about how you did them. So I have an example here. You know, my function is t cubed over t plus 1. So I applied the quotient rule. And so I wrote what the quotient rule is, said, you know, g of t is t cubed and h of t is t plus 1. And so derivative of g with respect to, I used g prime. Shouldn't have used g prime, right? Should have used g dot. What was I thinking? Anyway, derivative of g with respect to time is 3t squared. Gave my long word for it. Derivative of h with respect to time is 1. And then using the quotient rule, getting to my final answer. Right, so I want you to do that kind of process for each one of these A through E. And you're going to be using things like product rule, chain rule, exponential rule. Question?
Is it a line?
I believe it is already. If not, it will be.
Then what is it?
It will be due next week in class, what I'm going to have you do is each person will choose two problems, one that's a derivative and one that's an integral, and illustrate their solution in class. And then the next week you have to turn it in. So after everybody has shown their solutions, you still have another week to polish it up and turn it in. So 2 weeks from today. Okay, then the second page is integrating the same functions. And one of those requires you to use L'Hopital's rule. And once again, sitting in on Nathan's class last year, I know that you guys use L'Hopital's rule. And one of these integrals here, you have to use L'Hopital's rule. And notice this last one. To do this one, you either need to have incredible foresight, which I don't have, and I assume that you don't have, you might, or look it up. So I recommend use Wolfram Alpha or similar tool to find the indefinite integral. That is to find the integral of f of t with no limits. and then use the fundamental theorem of calculus to confirm that it's correct. So this one here is, going to be a little more work to solve. Because, looking at that offhand, I'd be like, ooh, I don't want to. Okay, so if you have questions with these, feel free to contact me. I will help you, right? It's not like I want you to go and bang your head on walls. I want you to remember things. If you can't remember, come talk to me so we can work together for you to remember or learn if you never did quite pick it up. Everybody good? All right.